All right, so now let's get into looking at the concentration of these hydronium and hydroxide ions that were formed by dissociation of our acid or our base. So similar to what we looked at before when we looked at concentration, is that it is expressed in molarity, at least in chemistry. This is the most prominent way that we will look at it. And molarity is, if you recall, moles of the substance per or over how many 1 liter of solution. So what is great about this is that we will use stoichiometry for this. So we're going to be looking at those mole ratios that we just talked about back in the stoichiometry unit. So when we are looking at the concentration of dissociated ions, it might be the same as our starting compound if we have a 1-to-1 mole ratio. And if our mole ratio is not 1-to-1, then it's not going to be the same. So we need to make sure that we can do the stoichiometry. So we're going to take a second. We're going to look at the concentration of these ions at the particulate level. All right, so this is a PhET simulation, and you could go to it too. It's the acid-base solutions PhET. And what I wanted to just kind of look at is down here we have our metal, M stands for metal hydroxide. So this could be potassium hydroxide or sodium hydroxide or lithium hydroxide. It's any metal. M is signifying that. So we have this compound and it's dissociating in solution to my metal ion. So this could be my lithium, my potassium, my sodium, whatever the case is, and the hydroxide. So when I look at the molecules here, and we can see that I don't have any of my original compound. They have all dissociated into my orange metals. We can see here my orange metals are all individual, and my OH, so my 2 blues, are my hydroxides. So this is when we're looking at a strong base. And we can also, if I add in, normally we have a strong base plus water, right? Remember when I crossed those off and we said, well, there's water there and there's going to be water here. Well, water, if I add in this solvent, we can see that the water, the H2O, the gray water compound here, is mixed all up in there. Water is surrounding my metal ion, water is surrounding my hydroxide. We can see all of the waters all in there surrounding them, but we don't see any of this. And we can also see that by if I looked at this graph. This graph is showing the concentration, moles per liter, which is molarity. We can see that, oh yes, my metal hydroxide is undetectable. And we can see that it has dissociated into equal amounts of my metal ion, my metal cation, and my hydroxide anion. And what we're going to look at here in just a second is we can see that this chemical reaction is balanced, right? I have 1 M on the left and 1 M on the right, 1 O and 1 H, and 1 O and 1 H. So everything is a 1-to-1 ratio. So therefore, I will have this, whatever concentration of M I have will be the same concentration as my OH. Okay, so now that we have looked at the particulate level, let's look at how to calculate the molarity of this OH ion. So first we need to write out the reaction. So number 1, write the reaction. So we've got KOH, that's a solid, added with H2O, that's a liquid. So we're going to have my K plus dissociate, and it's going to be surrounded by that water. And we are going to have my OH hydroxide, also aqueous. And again, it's going to be surrounded by water. And that H2O, it's just going to be there. I'm going to write it there just so we can see that my H and O, I'm just going to do that because we can't, remember, matter cannot be created or destroyed. So I can't just lose that water. That water is still there. We just didn't, it just isn't reacting. It's being used to disassociate that KOH into our metal ion and our hydroxide base. So then what we're specifically looking at here is that I am told that the concentration for my KOH, so my starting KOH, is 0.500 capital M, which means, I'm going to write this out, 0.500 moles of KOH for every 1 liter of solution. All right, I want to know the concentration of the hydroxide. So I am going from KOH and I want to know to OH. So it's important to then look at my mole to mole ratio. And if I look at KOH, so I'm going to say KOH, and I want to compare it to OH. I need to look, first of all, make sure that it's balanced. On the left, I have 1K, and on the right, I have 1K. All right. On the left, I have 1 OH, and on the right, I have 1 OH. On the left, I have 1 water. On the right, I have 1 water. So everything's balanced. Everything's a 1-to-1 ratio. So I can say that 1 to 1, 1 mole of KOH is equivalent to 1 mole of OH, which means I can then write my ratios here, and I can say 1 mole of KOH for every 1 mole of OH, or I can say 1 mole of OH for every 1 mole of KOH. So which one am I going to need to use here? Well, since I have moles of KOH on top, I need to have moles of KOH on the bottom, which means I need to use this ratio, not that one. So we just said 1 mole of KOH, and on the top, 1 mole of OH minus, there should be a minus. So then, because my moles of KOH will cancel out, I will have 0.500 moles of hydroxide over a liter of solution. And because we know that moles per liter is molarity, I can then say that this is equal to 0.500 capital M molar of OH. So because we have a 1-to-1 mole ratio, we can see that the concentration that I started with is going to be equal to the concentration that I am finishing with. So for this example, we are looking at calcium hydroxide dissociating in the water. So we can write this and we can say, okay, calcium is going to dissociate from the hydroxide. And I'm just going to leave out the water. We know the water is going to be on both sides. But we also know when we look at the periodic table that calcium is in my second family, my second column in the periodic table. And so it has a 2+ ion charge. We can also see that here because when calcium hydroxide was written, it had to give me 2 hydroxides because each hydroxide we know is a -1. So calcium will split into 2+, my hydroxide will split into -1. So when we balance this equation, we can see on the left that I have 1 calcium, but that I have 2 OHs. So we need to have 2 OH minuses here. So now we have a balanced equation. Now let's go and look at this concentration. We've got the same starting, so I've got 0.500 capital M of calcium hydroxide, which is the same as 0.500 moles of CaOH over 1 liter of solution. So now we need to compare calcium hydroxide to hydroxide. So we are comparing this to this. And if I want to look at that mole ratio, I'm going to say that for every 1 mole, because there's an implied 1 right there, 1 mole of CaOH2 for every 2 moles of hydroxide. And so therefore, for every 1 mole of those, there's 2 moles of OH minus, or I would use 2 moles of OH minus over 1 mole of CaOH2. So it's going to be one or the other. So then down here, now that I've got my starting written, because remember, I'm starting with the only number it's given me, I got to get to hydroxide, which means I got to get rid of moles of CaOH2. So I got to have that on the bottom. CaOH2, or in my denominator. And that would not be this guy. I need to use this conversion factor. 1 mole of calcium hydroxide for every 2 moles of hydroxide ions. So those will cancel. And then we need to do 0.500 times 2 divided by 1. So this would give us 1.00 with 3 sig figs moles of hydroxide over 1 liter of solution. So 1 divided by 1 is going to give us 1.00 capital M molar of my hydroxide ion concentration. Okay, so we are going to take a quick look at a strong acid example. Here we know that it's an acid because it's starting with H, and that we are going to get a hydronium ion once the H from HCl donates itself to water. So I'm going to have an H3O plus hydronium in aqueous solution, and that's going to leave my chlorine ion by itself. So we're going to take a quick look back at that PhET simulation to look at this at the particulate level. So here is our reaction, just like what we were looking at. I have my HA, so for example, my HCl, my A stands for my anion. So here's my hydrochloric acid plus water, and then this gives me my anion, so my, let's say my chloride ion, anion, and my hydronium. So if I look at the particulate level, then I'm able to look and see how my anions are disassociated from the acids ion. The chlorides are by themselves, and the hydronium ion is also disassociated. So we can see that since water is part of the reaction, if I click on my solvent, that water is surrounding all of those ions as well. And if I looked at the graph, we can see that water this time is being measured because it started off quite high, but as it reacts with the acid, because we know that this H from the acid is being donated to the water to create this hydronium. So the water is getting smaller and smaller as it reacts with that original acid. Okay, so if we get back to this problem and look at the calculations here, I forgot to add that my chloride ion was in aqueous solution. Let's look at solving this. We're told that I have 0.100 or 0.120 molarity of HCl. And so we're starting with my concentration of my acid, and I want to know the concentration of my hydronium ion. So we are going from a reactant to a product. And remember, whenever I have a chemical reaction, I have to look to see if it's a balanced reaction first. So I'm going to take a quick pause and do a quick check across the board. So I have one H and one Cl on the left. And, I'm going to look over here and go, I have 3 H's. Oh, wait a second. Actually, I have 1 H and 2 H's. So I have 3 H's on the left, 3 H's on the right, 1 O on the left, 1 O on the right, and 1 Cl, 1 Cl. So everything is balanced. That means that every coefficient is 1. Okay, so if I want to compare these two, I would say that 1 mole of HCl goes with 1 mole of H3O plus. So if I'm going to write those ratios, 1 mole of HCl over 1 mole of hydronium, or I would say 1 mole of hydronium is equivalent to 1 mole of HCl. So I need to use one or the other, okay? And so I'm going to do an or here. So if I have 0.120 molarity of HCl, remember that that is equal to 0.120 moles of HCl for every 1 liter. And then I need to choose that ratio that has moles of HCl on the bottom, which would be this guy. And again, it's a 1-to-1 ratio. So those are going to cancel, and I will get 0.120 moles of H3O plus over 1 liter, which is equivalent to 120 capital M molarity of my hydronium ion concentration. So next we're going to look at an example where it's not a 1-to-1 ratio. So if we look at this example, I've got H2SO4 plus water. So we can see here that we know that H is always a +1 and SO4 is -2, which is why there's 2 H's here in order to balance that compound. So we also know that acids like to donate that H, right? Because we want to end up with H3O plus. Well, if there's 2 H's here, it's going to create that H3O plus, and it's going to separate here, right? And that's aqueous. And it's going to give us our SO4 2 minus, also aqueous. So when we go to balance this reaction, we can say, okay, I have an SO4 on the left, I have an SO4 on the right. Okay, that's good. But on here we can say I've got 2 H's plus 2 H's is 4 H's, and on the right I only have 3. So we can say, well, the 2 H's that this wants to give away, it needs to go to two, create two hydroniums. And then we can do a quick check and say, well, how many H's are on the left now? And I would look and I'd say, oh, I have two H's plus plus four H's, right? If I have two waters, that's four H's. Plus two H's is six H's on the left. And on the right, this giving me two H3O's is six H's. So now I'm balanced. So now we just need to compare my H2SO4 to my hydronium ion concentration. Let's look at those mole ratios. I would say for every 1 mole of H2SO4, there are 2 moles of H3O+. So again, to write those mole ratios, I can say 1 mole of H2SO4 for every 2 moles of H3O+, or 2 moles of H3O+ for 1 mole of H2SO4. So either one of those. So now we're just going to start with my given concentration. So the same as what we were just using, 120 moles of H2SO4. Again, I know it gave us capital M molarity, but remember that is moles per liter of solution. So then I just need to figure out, well, which of these am I going to use? I got to have moles of H2SO4 on the bottom. So I'm going to use my 2-to-1 ratio here. H3O+. And make sure that those cancel. So 2 times 0.120. So we can see with our final answer that we got 0.240 molarity, capital M, of hydronium. And so all of these examples have been with strong acids and bases. So we can see that the concentration of these hydronium ions or hydroxide ions are either the same as what I started with, if it was a 1-to-1 ratio, or the concentration is greater for the hydronium or hydroxide concentrations and this is again for strong acids and bases. So in summary, if we look at reviewing, we know that molarity is moles of the species per liter, moles per liter, that we need to look at the stoichiometry or the mole ratios. We have looked at the dissociation of our strong acids and bases and how if it's a 1-to-1 ratio that our concentration is the same as what we started with, or it is higher. If it is not a 1-to-1 ratio, it's going to be greater than.